and pointed out that I've been negligent in posting the video since I came back. My fault. In my absence, of course, Mr. Mosen and company were taking care of this. I forgot. When you see things like this happening, you got to holler so that I can fix the problem. Also on bonus quiz number 2, which is now available, I believe the second part of question 1 reminds you that the system volume is made to 1 liter. If that's not there, I'll take a look to make sure that it is there. Because again, I want moles and molar concentrations to be numerical equivalent so that you can focus on the chemistry and not have to be paying attention to too much arithmetic. If that's not there, I'll fix it, but I think it's there. If it's not correct as posted, I'll repost and put a message on the website. In any case, back to developing our short half-reaction table. Sodium reduces vigorously to violently water. From that we got half reactions 1 and 2 over there. Zinc, not oxidized by water. Now the truth of the matter is, if you look at the half reaction information, you'll see that zinc metal is oxidizable by water. Why doesn't this reaction go anyplace? Why is it fair from a practical fashion to say that zinc is not oxidized by water? Well, the practical result is if we put a piece of zinc in water, we don't see anything happening. That's because zinc, pure zinc, will be oxidized by water to form a very, very thin coat of zinc hydroxide, which would stop the reaction because it would protect base metal zinc from further contact with oxidizer water. So practically, this reaction doesn't go anyplace. But zinc in 1 molar sulfuric acid solution we saw is readily oxidized. What's the difference? You're not going to make any zinc hydroxide coat in this strongly acidic solution. So fresh zinc is always exposed to hydronium ion in the sulfuric acid solution. So since our PSI is hydronium ion, hydrogen sulfate ion, water, we recognized, for reasons just stated, water is not the oxidizer. And as it is the case when sodium reduces water, we get hydrogen. When zinc reduces hydronium ion, we get hydrogen again. This shouldn't be surprising, because hydronium ion is compositionally just like water. And so when we run this and see a gas liberated, recognizing that the gas is produced from the component elements of water in the case of sodium, hydronium ion in the case of zinc, the obvious gases derivable from these two species are hydrogen and oxygen. And we demonstrated yesterday that by simple oxidation number analysis, you do not reduce water or hydronium ion and produce oxygen. You can oxidize water or hydronium ion and produce oxygen, but you can't make oxygen by reduction. Why not? Water, hydronium ion, oxidation state of oxygen, -2. Elemental oxygen, oxidation state 0. Well, if water or hydronium ion is the oxidizer, and therefore gets reduced, I can't take, by reduction, a -2 oxidation state oxygen and turn it into 0 oxidation state oxygen. Because when something gets reduced, oxidation states go down. They don't increase. So if nothing else, this simple oxidation number consideration tells us that just like in reducing water, when you reduce hydronium ion, you also get hydrogen. We could, of course, trap the liberated gas, if we wanted to confirm this by experiment, analyze it, and in so doing find out that it is indeed hydrogen, not oxygen. So, how did we decide that it was hydronium ion rather than hydrogen sulfate ion, which was the oxidizer? Well, if we're making hydrogen, then we're going to make hydrogen by reduction from the best source of +1 oxidation state hydrogen. That's H+. And hydronium ion is a stronger acid than hydrogen sulfate ion. So look what we've now recognized. The production of hydrogen by redox depends on pH. Zinc in water. What's the pH? Straight water. pH 7. Hydronium ion is there. The concentration is very small. Zinc, 1 molar hydronium ion. What's the pH? Well, what's the pH? Are we frozen in space? 1 molar hydronium ion, pH 0. So pH 7 water, we're not producing hydrogen by redox. At least not with zinc. But pH 0 water, or more particularly 1 molar sulfuric acid solution, 1 molar hydrochloric acid solution, 1 molar nitric acid solution, hey, we're producing hydrogen by redox. So, we find out that the oxidizing power of a system, because hydronium ion is the oxidizer here, water was the oxidizer with sodium. The oxidizing power of a system increases as system pH increases or decreases. Zinc, pH 7, no redox. Zinc, pH 0, did we oxidize zinc? Do we have to do it again? Zinc, pH 0, ready oxidation of zinc as hydrogen is produced by reduction of hydronium ion. So how does the oxidizing power of a system depend on pH? I'll ask you stuff like this on the next exam. You can bet on it. Look at the half reactions. Look at the table in the notes. Take a look at oxygen, if you will. Oxygen is a particularly good oxidizer. Now, for the investigations we've so far done, we haven't looked at oxygen as an oxidizer, but you can look at oxygen as an oxidizer by looking at the half reactions. Look at the half reactions which involve oxygen. There's 3 of them in the table. See if you can find them all. One of them is occurring at pH 7. It's not a standard half cell. It doesn't have an E0 value. The information in the table tells you this. It's in there for the sake of comparison, to get at the comments we're presently making. To see, in this case, how the oxidizing power of the system depends on pH. Did you find these half reactions which involve oxygen? Now the half reactions as they are written show reducer on the left becoming oxidized to conjugate oxidizer on the right. So for the half reactions which involve oxygen, if you want to use these half reactions to compare the strength of oxygen as an oxidizer as a function of pH, you have to take the half reactions which contain oxygen and look at them in the opposite direction. Because then you're seeing oxygen behaving as an oxidizer, where oxygen is consuming electrons and getting reduced. How do the E0 values for these half reactions compare as a function of pH? Look at them. Look at the notes. Let this stuff talk to you. Find the half reactions? Because if you want to take this entire table of half reactions and write them as a series of oxidizing half reactions, you've got to take the entire table and write every half reaction in the opposite direction. And when you write every half reaction in the opposite direction, what do you do to the sign on E0? You change it. If it's minus, it becomes plus. If it's plus, it becomes minus. So are you seeing the half reaction with oxygen? Do you see how its oxidizing power changes as a function of pH? Does it become a stronger oxidizer or a weaker oxidizer as you make a system more acidic? What's this stuff tell you? Well, talk to me. What's this information tell you? Oxygen is becoming a much more potent oxidizer as you make the system more acidic. You think this might have something to do with practical chemistry at home, like food spoilage? It sure does. The spaghetti sauce. You like spaghetti? You ever do spaghetti sauce? You buy a can of spaghetti sauce, jar of spaghetti sauce at Publix, and open it, you use some of the sauce and then recap it, put it in the fridge. The spaghetti sauce spoil readily, or does it have a habit of staying okay for a good long time? What's your observations tell you? Stay okay for a good long time or spoil readily? Stay okay for a good long time, you betcha. Is spaghetti sauce acidic or basic? What's spaghetti sauce made with principally? Pickles? How about tomatoes? You think tomatoes are principal component of spaghetti sauce? Are tomatoes acidic? You're damn right. That's why this system stays happy and healthy for a good long time. Because it's a but it's a fairly good oxidizing system because it's acidic. So if bad bugs get in there, the bad bugs get oxidized. That kills them. How about that? But if you take basic foods, or essentially pH neutral foods, they don't last very long. Because now the bad bugs get in there, there's no oxidizing stuff to kill them. How about that? In any case, back to this. If hydronium ion is reduced by zinc to make hydrogen as the gas product, we have to recognize there's got to be another product, because so far none of the product contain oxygen. Question. From one hydronium ion, can I make one hydrogen molecule? Theoretically, from one hydronium ion, can I make a hydrogen molecule? Yes or no? Can you count? How many hydrogen atoms do I need to make a hydrogen molecule? 1, 2. How many hydrogen atoms have I got here? 1, 2, 3. Now then, is it the case when zinc reduces hydronium ion that I get both the hydrogen atoms from a single hydronium ion to make the hydrogen molecule? Yes or no? When zinc reduces hydronium ion, do I get both the hydrogen atoms from a single hydronium ion? Well, these are +1 oxidation state hydrogens, aren't they? So let's start by taking away a single +1 oxidation state hydrogen from hydronium ion. We know that keeps with its chemistry because we know this is a strong acid. It's an H+ giver. What do I have left after I take H+ from this? Zinc reduce this? Does zinc readily reduce this? No. So what's this telling us? To make my hydrogen molecule by reducing hydronium ion. Can I get away with just one hydronium ion, or do I need more than one? One or more than one? One or more than one? More than one, because when I take away one H+, I got water. And we've already found out water is a much weaker oxidizer than hydronium ion. Water is not oxidizing zinc, practically speaking, but hydronium ion readily oxidizes zinc. Folks, this is strictly and exclusively a game of logic. That's what science and chemistry is all about. That's why I do this stuff all the time, and I'll never stop doing it. You got to think about this stuff. So, 2 hydronium ions. Now I have readily available 2 +1 oxidation state hydrogens to clobber with electrons to give me my 2 H atoms, which glue together and make my H2 molecule. And when I subtract H+ from each of these, what do I get? Water. And now I have material balance, because I paid attention to the material components of the system. What remains is to establish charge balance. 2 moles plus, no charge on the right, so the multiplier's got to be 2, and so I take this half reaction, write it in the opposite direction, so I can in a systematic fashion add it to my table, and here's half reaction number 4. Now, copper. We wish to consider the oxidation of copper. Statement, which we made yesterday. One of the opening rules regarding development or derivation of half reactions is that if a metal is oxidized in water solution, unless you're told otherwise, it's going to be oxidized to a hydrated metal ion. So for the cases of oxidation of copper that we are going to look at right now, here's what's going to happen. Copper is going to become hydrated copper ion. And you know what hydrated copper ion looks like. We showed it to you yesterday. And in lab, if you're in assignment 6, anybody in assignment 6 lab? You ought to be there by now. You know what hydrated copper ion looks like. What's it look like? What's it look like? Stand up. You're a little bit more blue than hydrated copper ion, but this guy's t-shirt looks a lot like hydrated copper ion. Okay? Thank you. We'll pay you later for your services. Now then, here we have some investigations with copper. Early on, before we even started to talk today, I put a strip of copper in 9 molar sulfuric. Nothing going on. Well, do you think it's fair to conclude that if 9 molar sulfuric will not oxidize copper, then 1 molar sulfuric surely won't do it? That's pretty fair. The 9 molar sulfuric inventory is the same way, but it's 9 times as concentrated. Now, I got here a second zinc strip. As usual, for me, it's got chalk particles on it as well. I'm going to put some 6 molar nitric acid solution in this beaker. So I now have a system which in fact is copper strip standing in 6 molar nitric acid solution. PSI? You tell me, I'll write it. Here again is the beaker in which a copper strip is standing in the presence of 6 molar nitric acid solution. See any color beginning to develop?
Yes.
What's the developing color indicating? Copper is being oxidized to hydrated copper ion. What do you think is going to happen to the intensity of this color as this reaction continues? Going to increase because we're going to put more and more copper ion in solution. Now then, what's doing the oxidizing? Is it water? Zinc does nothing with water. Copper does nothing with water. Copper's a poorer reducer than zinc. We already know that. Is it hydronium ion? Copper does nothing in 9 molar sulfuric. I got it over there. Copper not oxidized in 9 molar sulfuric nor in 1 molar sulfuric. Is hydronium ion doing this oxidizing? Heck no. Why should 6 molar hydronium ion do the oxidizing if 9 molar hydronium ion can't do it? Well, guess what that leaves? Same game, PSI, you got to pay attention to it. Now, to expedite matters, given that the gas which is produced by this reaction is not a nice gas, I'm not going to run this for any length of time. If you look at the surface of the copper strip, just as I asked many of you yesterday to look at the surface of the zinc strip when it was standing in the 1 molar sulfuric acid solution. If you look at the surface of this copper strip, you will see bubbles being liberated readily. Bubbles of gas. We've already recognized the development of this blue color, which is characteristic of the production of hydrated copper ion. So we know this is going. Now I'm going to shut this down. Because again, the gas itself which is produced by the reaction is not particularly noxious. I will offer more comments on this in a moment. The gas produced by the reaction, however, when it comes in contact with atmospheric oxygen, then it makes a noxious gas, NO2. We don't want that. Now, regarding derivation of half reaction, that's what we know so far. We saw a gas being produced. We know nitrate ion is the oxidizer. So we're right. We've written down what we know so far. Now perhaps you recall that I've reminded you by past conversation that nitrogen is capable of forming a whole bunch of different gas materials. And in the presence of oxygen, you think it's fair to say this nitrogen is in the presence of oxygen? It's covalently connected to 3 of them. I can make N2O, I can make NO, I can make NO2, I can make N2O3, I can make N2O4. And every one of these products involves the reduction of nitrate ion. Because if you look at the oxidation state for nitrogen in every one of these products, you'll see it's a lower value than the oxidation state for nitrogen in nitrate ion. More on that in a moment. So, to find out what this gas is, we'd really have to catch it, trap some, and analyze it. We'd find out it's this. Okay? Nitric oxide. Now, nitric oxide itself is not particularly noxious, but nitric oxide, when it comes in contact with molecular atmospheric oxygen, will convert rather readily to this, which is a brown gas. If I let this go for any length of time, you'll see this gas turning brown. But this stuff is rather noxious and poisonous, and I don't want that. Not in our atmosphere here. Okay? How do we develop a half reaction equation from this information? What do we do now? Do you see that what we have on the board tells us that as nitrate ion converts to NO, two oxygens previously bound to nitrogen go someplace? Where do they go? How can we find out? What do you think we might do for nitrate ion to give us a handle on finding out what the fate is of these oxygens which appear to disappear? What should we do for nitrate ion? Yes! After determining the product gas is nitric oxide, NO, we recognize that for the parent nitrate ion, how many NO bonds have to break? 2. How do you expect these NO bonds to break? Bond breaks here, bond breaks here, or bond tears in half. How do you expect these bonds to break? We did this when we used Lewis structure analysis to give us an idea on the best way to get oxidation numbers. How do we break the bonds? All the electrons go to oxygen. Why? More electronegative than nitrogen. How about that? So let's break this bond, and let's break this bond. Now, after breaking these bonds, I see that these oxygens, which are liberated to the system by this reaction, bear what oxidation state? What's the oxidation state for these oxygens? Look at the picture. What's the oxidation state for each of these oxygens? -2. Quotes, because these are not charges, these are oxidation states. So I'll write this -2 oxidation state oxygen like this. This look like a formula you're familiar with? You know anything about the chemistry of this thing? You got your acid-base table? Get it out. You see this formula in the acid-base table? Where do you see it? The acid-base table tells you that in our acid-base table, this is the strongest base shown. Name oxide ion. So, in fact, what's happening as I run this reduction of nitrate ion to NO is I'm putting -2 oxidation state oxygens into the system, oxide ions. What do we know about oxide ions? They're very potent bases. If a very potent base is put into a system, with what will this potent base react? I want the answer that's always correct. The strongest acid present in high concentration in the system. Do you agree with this? There's our PSI. Do you wish to tell me what the strongest acid is in this system? Does this look like it? How about that? So, let's go back to nitrate ion and recognize that beside nitrate ion, hydronium ion is a reactant in this system. Because as this is torn apart to give us oxide ions, -2 oxidation state oxygens, the species which gobble up these oxide ions are hydronium ions. How many -2 oxidation state oxygens are being put in per nitrate ion? 2 of them. How many hydronium ions do we need to clobber these 2 oxide ions? Well, let's do this. In strongly acidic solution, do you agree that 6 molar nitric strongly acidic? In strongly acidic solution, 1 oxide ion beats up how many hydronium ions? Don't tell me 1. Because if I take 1 H plus only and give it to oxide ion, what am I making? Hydroxide ion. You can make hydroxide ion in strongly acidic solution? Not today, not tomorrow, not ever. So I ask again the question. In strongly acidic solution, 1 oxide ion murders how many hydronium ions? 2. And the products are? If I deprotonate hydronium ion, what do I make? Water. How many hydronium ions did I deprotonate? 2. And each of these protons landed on oxide ion, making me 3 waters total. How about that? So per nitrate ion, how many hydronium ions? If I need 2 to murder 1, then I need 4 to murder 2. And so I am recognizing that beside NO in this half reaction, how many waters am I making? You do have to count. How many waters? 6 waters. Right? Nothing fancy about this. So I have now, for this system, established material balance because I paid attention to every material component. Let's tidy this up. Since we've done the analysis necessary to allow us to get the half reaction developed from a material standpoint. The last part of the puzzle is to establish charge balance. What's the multiplier on electricity? Any charge here? No. That means the sum total of charge on this side of the fence has got to equal 0. Well, if I got 4 moles of plus and 1 mole of minus, how many moles of electricity do I have to add to make this thing electrically neutral? How many? And if you've not yet recognized it, when you put the correct moles of electricity in a half reaction, like we have over here, like for all the half reactions in our table, when you put in the correct moles of electricity, it always keeps with total change in oxidation number all the time. What's the oxidation number for nitrogen in this stuff? What is it? Tell me and I'll write it down.
+2.
What's the oxidation number for nitrogen in nitrate ion? Do we need to go back to the Lewis picture?
+5.
If I want to go from +5 to +2, I got to add 3 moles of electricity, don't I? How about that? This stuff works out so nicely if you do the analysis correctly. And to do the analysis correctly, you've got to pay attention to the chemistry of the system. And you do have to count a little bit. So, we've got our last half reaction for the simple table we're developing. Again, I'll write it in the opposite direction. Just took this half reaction, wrote it in the opposite direction, added it as half reaction 6 to our table. So this half reaction is telling us when I oxidize something with nitrate ion, like in this case copper, I may well need the assistance of hydronium ion. Let's pursue that with one more investigation. Here, I got 6 molar sodium nitrate solution, so this has got nitrate ion in it at 6 molar, just like our nitric acid solution. What we're trying to find out is, can nitrate ion by itself at a molarity of 6 oxidize copper? So we assembled a system. We know doggone well that if any oxidation of copper occurs in this system, here's the system. Six molar sodium nitrate solution is not going to be water, and it's certainly not going to be sodium ion. So if any oxidation again occurs of copper in this system, it's got to be nitrate ion doing the job. Now here, to remind you again, from the start of our talk today, I've got copper sticking in 9 molar sulfuric. Nothing going on. So 9 molar hydronium ion is not capable of oxidizing copper. And now I got copper standing in 6 molar nitrate ion. Nothing going on. Conclusion? If I'm going to oxidize copper with nitrate ion, do I or do I not need the boost provided by hydronium ion? Something to gobble up these -2 oxidation state oxygens as nitrate ion is converted to NO. That seemed to be fair? I need hydronium ion's assistance. Well, let's take this beaker, which has got the sulfuric acid in it, 9 molar, and here's the beaker, which has got 6 molar nitrate ion. All I'm going to do is to transfer some of this solution to this beaker. Because in this beaker, I now have a system which very much parallels this, except that it's also got hydrogen sulfate ion in there. But now I got high concentration of hydronium ion as well as high concentration of nitrate ion. Any color beginning to develop? Look at the surface of the copper strip. Is any bubbles developing on this surface? Little tiny bubbles. Lots of them. What do you think these bubbles are? What are these bubbles? What are the bubbles? Hello, gas! Just been through this analysis, haven't we? Oh, the reaction will continue and the copper ion color will get more and more intense, but I don't want to produce the gas because of its nasty nature. So we'll shut that down. Question. If with this simple list, simple in that it's a very short list of half reactions, I want to run a redox reaction of greatest vigor. Look at the list. With this information, and this information only, what is the most vigorous redox system you could assemble? What's the strongest reducer in this list?
Sodium.
There it is. What's the strongest oxidizer in this list? Here it is. Statement. If you wish to place a large chunk of sodium into a few hundred milliliters of 6 molar nitric acid solution, please let me know so I can get out of town before you make this mix. Because as soon as the sodium hits that 6 molar nitric acid solution, you are going to have one hell of a violent explosion. Be careful. Next question. From this short list of half reactions, how many redox reactions can have the thermodynamic outcome correctly predicted? From this short list of half reactions, 6 of them in total, how many redox reactions can have their outcome successfully predicted from a thermodynamic standpoint? Give me a number when you think you've got the right number. Predictable reactions from this list. How many? More than that. More than that. We're going to do this by guessing. We'll eventually get there. 37. How you came up with that one, I'll not know, and I'm not going to even ask. Let's look at the list. Can I predict sodium with water? Is that a go? Sodium with zinc ion? Is that a go? Sodium with hydronium ion? Is that a go? Sodium with copper ion? Is that a go? Sodium with nitric acid solution? Is that a go? You betcha. Everyone's a go. Now, hydrogen with hydroxide ion. Can I predict the outcome of hydrogen hydroxide ion with sodium ion? Is that a go or a no-go? It's a no-go, but I can predict it. Hydrogen hydroxide ion with zinc ion, is that a go? Hydrogen hydroxide ion, hydronium ion, is that a go? Of course. Every reducer on this side will reduce the conjugate oxidizer of all listed underneath this. Here, this reducer can't reduce this, but can reduce all of these. This reducer can reduce this and this, but not this, this, and this. So if I look at 6 reducers and 5 possible products, I can recognize that the number of reactions whose thermodynamic outcome is successfully predictable with this table is 30. 6 times 5. Now look at the half reaction table in the notes. How many half reactions in this table? How many?
45.
45 half reactions. Tell me the arithmetic you would do right now to use the table in the notes for reaction outcome prediction. What arithmetic would you do? Is that a fair number of reactions? That's a fair number of reactions. This table is a wealth of thermodynamic information. We just showed you one more way that you can use it. All right, what we will do now is to pick up on the lesson plan from Friday. Many of you will have heard what we're now going to discuss, but many of you will not have heard it because the different discussion classes made different degrees of progress. Now, cube. H plus source in basic aqueous solution. I want the answer that's always correct. What's your H plus source in any solution? Same thing here. Next question. Do you think that in basic aqueous solution, the strongest acid present in high concentration will commonly be water? Yes, it is. Now then, do you think in basic aqueous solution, the strongest acid present in high concentration is always water?
Yes.
You remember buffers? Is this an acidic buffer solution or a basic buffer solution? Basic. Ammonia is a much stronger base than ammonium ion is an acid. That's a funny way of saying Kb ammonia is a lot bigger than Ka ammonium ion. But in this quite basic buffer, the strongest acid is this, and that'll be your H plus source. So how do I always answer a question like this? It's called PSI, isn't it? There's no getting away from that. All right. So let's look at question 2212. Applying this to 1 molar sulfuric acid solution. gives oxygen at the anode. The question is, what's my source of oxygen atoms in this system to make the oxygen at the anode? Have you seen this symbol before? This means electrolysis. You think I can readily run an electric current through sulfuric acid solution? Can I readily run an electric current through sulfuric acid solution, 1 molar? You betcha. Why?
It's ions.
I got a high concentration of ions. That's what I got to have in a solution to run a current through it. So this is like running an electrochemical cell in reverse. In this case, I'm going to run a current through the system. I'm not going to make a system to give me a current. And when I run a current through this system, from this electrode, oxygen gas bubbles are liberated. Where am I getting the oxygen? What's being electrolyzed to give me the oxygen? What do we got to do for this system to get a handle on this? How about that? These are my oxygen-containing components. It's also all the components, except for a tiny concentration of sulfate ion. So which of these 3 oxygen-containing species is reduced by this electrolysis process, is attacked by this electrolysis process to give me the oxygens I need to make my oxygen molecule? Which of these oxygen-containing species is in fact electrolyzed to produce oxygen at the anode? What's your bet? What might you do to find out? Or to give you a chance to find out? I'm listening.
Lewis structure.
How about that? Come on, get at it. I want Lewis structures for all of these things. Isn't that the way we tackled the nitrate ion NO system? Are we happy with these Lewis pictures? Now then, you think it's a fair statement that the HO bonds in water and hydronium ion are practically speaking equal in strength. And clearly to get oxygen atoms to make my O2 molecule, I got to break these HO bonds. How do you think the HO bond strengths compare to the SO bond strengths in hydrogen sulfate ion? Would you bet that if hydrogen sulfate ion is the stuff getting electrolyzed, these are not the oxygen atoms which you're going to get? Why is that? Why would you bet these are not the oxygen atoms used to make the oxygen molecule? To set free this oxygen atom, how many bonds you got to break? 2, and one of them's an HO bond, isn't it? So you're not going to get this one. Here you only got to break 1. 2. 1, 2, 3. Pardon me, I didn't count correctly. What I meant to say is, let's get back to fixing this. How do the SO bond strengths compare to the HO bond strengths? What do you think about that? We'll write it down. How do you think these bond strengths compare? Which bonds do you think are stronger?
SO, because there's resonance.
Mm-hmm. So by recognizing SO bonds are resonance stabilized, we can realize that my oxygen atoms are going to be made available by electrolyzing either this or this. Now let's make a decision between these two. Is it more likely to get the O atoms by tearing up one of these, or instead tearing up one of these?
Water.
Why water?
Less bonds.
Fewer bonds. Here I got to break 3 HO bonds to give me an O atom. Here I only got to break 2. So this is what's getting electrolyzed. And in fact, getting electrolyzed to make oxygen at the anode. Here's my water molecule. And in this electrolysis process, think before you answer. Are the oxygen atoms being oxidized or reduced? What's the oxidation rate for oxygen and molecular oxygen? Well,
0.
what's the oxidation state for oxygen and water?
-2.
So are these oxygen atoms being oxidized or reduced? Being oxidized, aren't they? However, in this case, the oxidation is being fostered by the electric current, which are going to rip electrons away from oxygen. So, as usual, I will break up the water molecules in this fashion. The electric current will pump the electrons away from this and turn it into a zero oxidation state oxygen. But the purpose of the analysis is to realize that I must tear up how many water molecules to give me my 2 oxygen atoms to make an oxygen molecule? 2. And when I tear up the water molecules, at the same time I'm putting H pluses into the system. What will these H pluses react with? What will H pluses react with whenever you put them into a system? The strongest base present in high concentration in the system. In this system, what is the strongest base present? What is it? There's our PSI. What's the best base in this system? Look at the acid-base table if you need help. What's the best base in this system? Water. So I got to murder 2 waters by breaking these HO bonds to give me the O atoms I need to make the O2 molecule. And I need how many more waters to collect the H pluses? 4. So 6 waters are going to be part of this reaction. And beside making molecular oxygen, what else am I making? Didn't these waters collect the H plus? So, 4 hydronium ions. How many electrons total then are being liberated by this half reaction? No charge, 4 plus, 4 minus. Finally, we got this far. Note, H3O plus produced at anode. Wonderful. So now we can ask a question. As this electrolysis proceeds, does the pH of the system increase, decrease, or stay the same? The system pH delta for change as electrolysis proceeds. Now, before you try to answer this question, I want you to realize, have we or have we not yet paid attention to all the chemistry occurring in this system? Have we or have we not paid attention to all the chemistry occurring in this system? Have we or have we not? We have not. What haven't we paid attention to yet? I'm listening. What haven't we paid attention to yet? We're running an electrolysis redox reaction. We've recognized that in this redox reaction at the anode we're making oxygen gas. Okay so far? What haven't we paid attention to yet? How about that? What's going on here? What do you bet? Because we are electrolyzing water. And we are turning water at the anode into oxygen. So what do you think we're making at the cathode? What's water composed of? Hydrogen and oxygen. So we're making oxygen at the anode. What are we making at the cathode? Hydrogen. How about that? All right. Question. Here's my PSI. In this electrolysis process, what am I reducing to get molecular hydrogen at the cathode? In this system, what's the best source of +1 oxidation state hydrogens? There's the PSI. Hydronium ion, isn't it? How many hydronium ions do I need to murder to get my hydrogen molecule? We were through this just a while ago. How many? 2. And so if I murder 2 hydronium ions to give me enough H atoms to make me a hydrogen molecule, beside the hydrogen molecule, what else do I make? How many? And now I have material balance, so I look at this system and I see at a glance I need 2 electrons. We're still wrestling with the question. Does system pH change as this electrolysis proceeds? Here's what's going on at the anode. Here's what's going on at the cathode. If I wish to get the equation for the net overall redox reaction, can I add these half reactions as they stand? What do I have to do? Double this one, don't I? So that I got 4 moles of electrons liberated while 4 moles of electrons are being consumed. And when I double this one, what happens to moles hydronium ion? Becomes 4. So here's 4 moles hydronium ion produced. Here's 4 moles of hydronium ion consumed. Does the pH change? Huh? No. How about that? We'll pick it up from this point tomorrow.